All right, today we're diving into something pretty mind-blowing. It's a paper that suggests a whole new way to think about building AI. And this isn't just a small tweak. We're talking about an idea that could completely change how machines learn and, maybe, solve one of the biggest problems in AI today.
So let me ask you this. What if an AI could just keep learning forever? Without forgetting everything it already knows. Imagine a model that doesn't just get trained and then that's it. Instead, it evolves, it adapts, constantly, kind of like our own brains do. And believe it or not, this isn't some far-off sci-fi dream. It's actually the whole point of the new architecture we're going to break down right now.
And to really get why this is such a game changer, you've got to look at how most AI works today. Right now, our models are, well, they're pretty static. Think of them like a brick wall. Once it's built, it's built. The architecture is fixed. So what happens when you try to teach it something new? Well, it often just forgets the old stuff. It's a huge problem. The dream, this lifelong AI, is to build something totally different, something dynamic, that can actually evolve on its own and adapt to new info. More like a living brain.
Okay, so that brings us right to the heart of the problem. I like to call it the AI with amnesia. And seriously, it is a massive roadblock standing in the way of creating AI that can think and act in a truly general way.
Now, the fancy technical term for this is catastrophic forgetting. And honestly, it's pretty much exactly what it sounds like. When you take a standard AI and teach it a new skill, let's say task B, it has this nasty habit of just overwriting what it learned for task A. Poof, gone. Its ability to do that first thing just tanks. It's a total disaster.
The researchers in this paper use a really powerful analogy for this. They compare it to something called anterograde amnesia. That's a real neurological condition where someone can't form new long-term memories. Every new experience just seems to push out the old one. It's a pretty intense way to think about it, right? But it perfectly captures the limits of the AI we have today.
So, how in the world do you solve a problem that big? Well, as it turns out, and this happens a lot in AI research, the answer might be right inside our own skulls. The solution is totally inspired by the human brain.
And the magic word here is neuroplasticity. This is just the brain's incredible, mind-boggling ability to literally rewire itself. It forms new connections all the time, our whole lives. It's how we learn to play the guitar, or speak a new language, or even recover from injuries. It's the exact opposite of that rigid, static AI model we were just talking about.
And this really shows you the difference, plain and simple. On one side, you have that rigid AI model. Its connections are fixed. Once it's trained, game over. But then you look at the human brain. It's dynamic, constantly rewiring, making some connections stronger, getting rid of ones it doesn't need anymore. The whole goal here is to make our AI act a lot more like that brain.
Okay, so taking inspiration from the brain is one thing, but how do you actually build that into a working AI model? Let's get into the nitty-gritty of how this self-evolving AI actually works and tries to copy that neuroplasticity.
The core technology they came up with is called Dynamic Nested Hierarchies, or DNH. Now here's the absolutely critical part. This isn't just an AI that learns new facts. This is an AI that can change its own structure. It can literally decide to grow new parts, get rid of old ones, and completely reconfigure itself, all on its own as it's learning. That's a huge deal. So, the DNH model copies the brain's plasticity in 3 really clever ways. First, there's level addition. Basically, when it hits something new and complex, it can just grow new neural pathways to deal with it. Second, level pruning. Just like our brains get rid of old connections we don't use anymore to stay efficient, DNH can trim the fat and remove parts that are no longer useful. And third, something called frequency modulation. This is wild. It's kind of like the AI can adjust its own brainwaves to pay more attention to either stable, long-term knowledge or stuff that's changing really fast. It's so cool.
All right, that all sounds incredible, right? Almost too good to be true. But theory is one thing. The real question is, does it actually work? Well, let's look at the numbers and see what happened when they put DNH to the test. First up was a test on common sense reasoning. The kind of stuff that's obvious to us but really hard for computers. They put their model, which they called DNH Hope, up against some heavy hitters, including a big language model and even a static version of their own tech. And look at that. The DNH Hope model comes out on top with the best accuracy. That's a pretty strong sign that its ability to change its own structure is giving it a real advantage in actually understanding things. But honestly, this next chart is the real mic drop moment. This shows how much each AI forgets when it tries to learn continuously. See that huge bar for the static AI? That right there is catastrophic forgetting in all its ugly glory. Now, look at the DNH bar. It's tiny. It's so much shorter. This is the proof right here in black and white. The self-evolving design is working. It's actually holding on to old knowledge while it learns new things.
Okay, next, they tested how it handled just insane amounts of information. And in these long context tests, DNS showed a pretty big jump in accuracy. We're talking 5 to 10%. Now, that might not sound like a huge number on its own, but in the world of AI, that's a serious improvement. So what does that actually mean?
Well, it means this DNH model is way, way better at understanding and thinking about super long streams of text. I mean, we're talking about a chunk of information the size of a whole novel. It doesn't get to chapter 15 and forget what happened in chapter 2. And when I say long, I mean really, really long.
Just how long are we talking? Get this. The DNH model could handle a context window of 128,000 tokens.
Now, a token is basically a word or part of a word. So to put that in perspective, that's like the AI reading a 300-page book from start to finish, and then being able to answer a tricky question about something that happened on page 5. That is a massive step up from what most static models can even dream of doing.
So, yeah, the results are pretty darn impressive, but let's zoom out. What does this all mean for the future? What could we actually do with an AI that can learn and grow for its entire existence?
I mean, the possibilities here are kind of staggering when you think about it. Imagine a robot in your home that doesn't just bump into the new couch you bought, but actually learns and adapts to the new layout. Or what about a conversational AI that actually remembers what you talked about last week and the week before that and actually grows with you? You could have medical tools that are constantly updating themselves with the latest medical journals, or education programs that tailor themselves to a student's learning style over years, not just minutes. This is the kind of future a system like DNH could open up.
And that really brings us to the final big idea here. Look, this research is a huge step toward creating truly adaptive general AI, but it also leaves us with this pretty profound question, doesn't it? If we actually succeed in building an AI that can learn and evolve and change all by itself, what does it eventually become? That's definitely something to chew on.